Welcome to the closing keynote of ISC 2026. I'm Ryo Yokota. I'll be chairing this session. Thank you. So the closing keynote session will be given by Jack Dongarra, who needs no introduction. So I would like to thank everyone for coming to the closing keynote. Yeah, I'm supposed to have notes here.
Okay, I don't
oh, yeah, thank you.
Oh, those are my notes.
Oh, no, yeah. No, not
those are my notes.
Okay, well, maybe I'll try to
you have to wing
do it. Yeah, okay. All right. So everyone knows Jack, so he needs no introduction.
No introduction. Thank you so much.
Among his so everyone knows Jack is awardee of the Turing.
Who is he?
ACM Turing Award. But okay, so yeah, because I prepared notes and they're not appearing, so I'm not going to take too much of your time.
I'm sure they were good.
Yes, yeah, they were good. I had
oh, there you go.
Oh, there it is. Okay, it's a real pleasure and honor to introduce Professor Jack Dongarra. So Jack is a research professor emeritus at the University of Tennessee and a distinguished research staff member at Oak Ridge National Laboratory. His work on numerical algorithms, linear algebra software, parallel computing, and performance benchmarking has shaped high-performance computing for decades. Among many honors, Jack received the 2021 ACM Turing Award for his pioneering contributions to numerical algorithms and software that have driven extraordinary progress in computing performance and applications. Thank you. When I heard that Jack had never given a keynote at ISC before, I was genuinely surprised. I thought he would have given many keynotes already. So it's hard to think of anyone whose work is more deeply connected to this community. So it feels especially fitting that he joins us today for this closing keynote titled HPC in Transition. Please join me in welcoming Jack Dongarra.
I don't think I've ever had an introduction quite like that before. And so I have not given a keynote talk at ISC. And being the last speaker, it's a lot like benchmarking in the sense that everybody's looking at their clock and they're hoping for a fast time to solution. Okay, so I'm going to talk about a few things, HPC in transition. And you know these stories as well as I do. Generative AI has really reordered and changed the computing landscape, and primarily along three axes. The first one is along the capital investment. So AI investment is now a situation which is played with hundreds of billions of dollars. And that level, it really challenges even some of the largest nations. There's a computer in Tennessee, not at the lab, over in Memphis called Colossus 2, which is being put together. And it's going to have 1 million of these NVIDIA Blackwell 200 GPUs. The cost of that machine is around 30 to 45 billion US dollars. And if we take a look at the power consumption, the energy used by these systems, it's really staggering. So just that system in Memphis will consume about 200 gigawatts, and the cost is about 1.8 billion US dollars per year just to fire it up. And when we look at the market capitalization of various companies, so market capitalization, what are these companies worth? And I've tried to put together a slide which has a number of companies. We see traditional computing companies like Intel, HPE, IBM, AMD being dwarfed by these other guys, Facebook, Amazon, Apple, Google, and of course NVIDIA. NVIDIA's net worth is about $5 trillion. So incredible situation in terms of these companies. And HPC is now really being put together with generative AI. So we have this deductive world of physics-based modeling, PDEs, discretization, that's being augmented with this inductive world of surrogate models. So the hybrid model now allows for a rapid exploration of a parameter space as long as we have some understanding of what that model can the domain of acceptability. So training neural networks, of course, is an important process. Using AI surrogates to rapidly explore a parameter space is key. And of course, then having some numerically intensive simulation that can verify what was done by the AI system is really critical. And if we take a look at the situation with weather modeling. So last year we had a keynote, and that keynote talked about weather modeling and AI. And we're in a situation today where we can train those weather models using AI with 40 years of data that we have, and AI can predict pretty good a 10-day forecast, and it can do it in seconds. And rather than having that be done in hours using the more traditional deductive way of doing business. And ECMWF is now running in parallel with their physics-based simulation of the AI models themselves. And in biology, we know about protein folding. There was a Nobel Prize given for AlphaFold and other really impressive results for accurately predicting 3D structures. And today, people now consider this to be really a solved problem. And when generative AI meets something it hasn't seen before, that's when we have a situation which is potentially problematic. So typical patterns of data observation are easy in some sense, but they struggle with atypical patterns when they occur infrequently or rare. And what they tend to do, of course, is predict the next token from what they have. They combine familiar ideas, and they come up with solutions to the problem. But they can fail, of course, when we are in a situation where that prediction doesn't quite meet, when they have atypical situations, and we end up with wrong results or hallucinations with it. So when the ideas are applied to familiar ideas, everything works fine. But once we get outside of that domain, we actually end up with many problems. So energy and data movement, of course, is something that we're very familiar with. And floating point operations are not really the critical thing. And that's been happening for a long time. We can plot the processors and look at what the data movement story has been, and we end up with that diverging situation that's referred to as a memory wall. And today, the arithmetic operations are increasingly a small fraction of the total energy budget that we have, and we can see that in benchmarks. So this is the HPC CG benchmark that was talked about and run on the student clusters. When we take a look at the top 10 machines, Eric showed this slide on Tuesday, we see that for HPCG, we're only reaching a small fraction of the theoretical peak performance. So if we take a look at that last column, that for the number one machine, I'll just point out for the line shine machine, that's 0.8%. That's not 8%. That's not 80% of the theoretical peak. That's 0.8% of the theoretical peak. Not even 1% of the theoretical peak is being reached. And that's sort of an average, to be honest. We have a few machines that shine in this context. The machine, the Fugaku system, reaches 3% of the theoretical peak. And then there's a machine also in Japan from SoftBank that reaches 2.5% of theoretical peak. And again, the data movement is the key thing, which is inhibiting processing. So the floating point is generally free in this context. The other situation is that as the system scales, so does the power requirements. This is a graph here that's intended to show that today we're spending about 5% of all the energy that's being generated for our data centers, and that number is expected to grow. And the growth here is shown to be somewhere between roughly 7 to 12% of all the energy that's generated is going to go into these data centers in the not too distant future. So maybe we need a new metric to look at, and maybe that metric could be a joules per trusted solution rather than looking at flops as a way of doing business. Benchmarks are really looking behind. They're not looking forward. They provide us with mirrors to look at where things have been. And they don't provide us with levers that tell us what we should be doing in the future. And to quote, to paraphrase Mark Twain, we have lies, damn lies, and benchmarks. And the benchmarks really rarely drive technical changes. They have little power in influencing strategic decisions. And we have these aging benchmarks, and the top 500 is an example of one of those really quite old benchmarks. 34 years today it's been around, and we need a wider variety of benchmarks to really be looking at. So these benchmarks generally reward incremental changes rather than doing transformational alternatives. So when we take a look at how we buy a machine today, it comes down to something like this. These are the long poles, if you will. We buy in a system, we have a certain amount of money that we're going to spend on a machine, and we have a performance level that we want to achieve. So those are the two things that we're looking for. We put out an RFP for a machine, and vendors put together a system that meets that dollar amount and meets that peak performance level. And that is really what we get. And they do that using off-the-shelf components, because that minimizes the cost and potentially can drive the performance level high. And that situation results in a hardware application level imbalance. And what we really need to do is to treat the whole system in a much more effective way, looking at hardware, software, applications, coupling the design problems, and really doing what we refer to as co-design. So we talk a good story about co-design. So everybody talks about doing a co-design system. Co-design refers to simultaneously developing a machine that has hardware, software, and applications in consideration, getting the architects together with the mathematicians, along with the computer science people, and having them, along with the domain scientists, and having them design a machine that meets the needs of the domain scientists. And rarely does that situation really take place. The goal here is to optimize the system based on some mutual feedback from that group, from the applications people, the algorithm designers, the software engineers, and the hardware people, that we can effectively come up with a machine that can meet the challenges that we have. And in scientific setting, those co-designs are really an exception. And old codes adapted to the machines that we have really perform quite poorly over time, and that's why we see that 0.8% of peak performance. And there's some exceptions, I have to say. So one exception is the line-shine machine and the Japanese Fugaku system. And they both have engaged in co-design. They both have systems which reflect applications and looking at ways in which they could extend that. So in the case of line-shine, they have an ARM processor which was modified to have vector extensions as well as matrix extensions. And each CPU has relatively high bandwidth, memory associated with it, and large transfer rates in and out of that system to provide with quite good capability. And it does really beg the question, do we need GPUs in our machines, or can we get by with a system like the one that was designed in China for the future? So that's a question I think the community needs to look at and understand if, in fact, we can get there. So when we take a look at the systems that we have today, and this is through the eyes of the top 500, if we take a look at the 500 machines, 91% of the machines are using x86 architecture. Intel and AMD chips are being used to drive the top 500 machines. Of course, those machines are augmented with accelerators. And if we take a look at the accelerators that are on the machines, 87% of those machines that have accelerators are using NVIDIA accelerators. And of the machines that are there, 91% of those machines are using either Ethernet or InfiniBand as their interconnect with the system, 91%. So again, things are being driven by commodity techniques and solutions, and of course everything is based on Linux. That's not a big surprise. And that's unlike the HPC, the hyperscalers, the other side of computing, the cloud providers. They're building their own processors. They're building their own accelerators and their own interconnect systems. If we take a look at those machines that are coming from Alibaba, they have a CPU that's based on an ARM architecture. Amazon, they have a machine that they've put together, again, using an ARM system. Google has their TPUs, and Microsoft has their Maya architecture. Those are all systems designing CPUs specifically for the needs that they have. They have the resources, that's where that net worth comes into play, and they can effectively drive that. And that's really unlike what we see in high-performance computing, where we're constrained by the use of these commodity processors. And there's sort of an industry now looking at AI and companies designing technology to effectively do that, and doing a pretty good job of that today. The next thing that we see are AI factories. So here we're in a situation where, again, the competition with what I would call traditional high-performance computing is quite striking. These hyperscaler clusters between 100 and 300 megawatts of power, and we see them being driven here in Europe, as well as starting up in the US. In the US, there was a project that was put in place in November by the president through an executive order to launch something called the Genesis mission. And the Genesis mission was launched as a national effort to apply AI and provide transformational scientific discovery. The executive order explicitly invokes a Manhattan-style level of project, mobilizing for AI-enabled science. The goal is to build this integrated AI platform to harness federal scientific databases, train scientific foundational models, and deploy AI agents, and basically get things in a point where it can be used effectively. However, no money was provided by this executive order, so that's the downside. The plan is to put in place a system, the next big machine at Argonne National Lab, just to give you a feeling for what's planned. The next big machine at Argonne is a machine that'll have roughly 100,000 Blackwell GPUs, be about 200 megawatts, be placed at Argonne National Laboratory. The performance is expected to be about 2 zettaflops of performance. Now, that's not 64-bit performance. That would probably be 16-bit or 8-bit floating point performance. The networking would be built on top of NVIDIA's system. The software stack would be NVIDIA's by design. And this is one of these situations that there's a partnership between the Department of Energy, Argonne National Lab, NVIDIA, and Oracle. So this is a private-public partnership that's being formed with the Genesis mission, where the machines are being put in place on government land. Power most likely would be supplied by the DOE, and those machines would be purchased by Oracle and be run by Oracle using Oracle's software stack mainly, and cycles from those machines would be sold as well as given to the Department of Energy to run its applications. So it's a quite different model than what we're accustomed to, and it's seen as the way forward in this public-private partnership. So energy and data movement, not floating point operations, are the thing, the scarce resource. Hardware designed for AI is already focusing on reducing the precision to reduce energy and data movement costs overall. And we traditionally think of doing scientific computations using 64-bit floating point, maybe 32-bit occasionally, and the systems that are coming out with have 16-bit, 8-bit, 4-bit, and the potential for doing emulation using integer arithmetic. Now, we have some tools available to us that can help use some of those characteristics. Tools like iterative refinement or systolic rounding or randomized sketching or hierarchical preconditioning. All of these things can benefit from the reduced precision and be used to drive some of the algorithms and applications. And we also have communication avoiding and energy aware algorithms that fit into this space. But if we take a look at what's happened here, this is looking at NVIDIA and looking at the Hopper. Hopper was put in place around 2022, and what I'm showing here is the performance, peak performance, for 64-bit FMA instruction. So it's a floating point multiply add instruction, simple instruction. And for the Hopper system, the peak performance was around 33 teraflops. And NVIDIA, of course, has a tensor core. When you see the word tensor core, think matrix multiply. So for matrix multiply, 64-bit, the performance went up to roughly doubling that. So 67 teraflops was the peak performance for 64-bit. 16-bit tensor operations enhanced the performance quite a bit. So now we're roughly at 989 teraflops of performance for 16-bit floating point operations. And if you can get by with integer operations, the number goes to around 2,000 teraops per second. And the memory system can absorb about 4.8 terabytes per second. That's the peak performance. If we go forward 2 years, what we see is Blackwell. Now, Blackwell enhanced things, and the enhancement was that the FMA instruction went up a bit. It went from 33 to 40 teraflops. The tensor core, the matrix multiply operation for 64 bits, didn't go up, it went down. So it went from 67 teraflops to 40 teraflops. The 16-bit tensor cores got a bump up, almost double. And the integer operations also went up considerably, another doubling. And the bandwidth went up, not quite doubling, but not bad in terms of the overall performance. So 16-bit operations are being used, of course, for AI applications mainly, and we see the effect there for the AI and integer 8 operations as well. And if we go forward again, to the Rubin processor, which is just now here, we see an interesting situation. The 64-bit FMA instruction goes down. It was at 40 and it went down to 33 teraflops. The tensor core, that also stayed at 33. So they don't really have hardware to do that matrix multiply. They're using the FMA instruction hardware to do that if you invoke a tensor core, 64-bit tensor core. The 16-bit tensor cores have gone up, again, almost doubling in terms of performance. Interestingly enough, the 8-bit integer operations have gone down. So 8-bit became out of favor with AI and focusing more on 16-bit and perhaps even 8-bit floating point. And the result of that is the hardware support for the integer operations has gone down. And fortunately, the bandwidth from memory has gone up. So we get an enhancement of memory bandwidth roughly 2.5 times for that. So the hardware situation is not in good shape, I would say, from the standpoint of 64-bit floating point operations. We don't see an enhancement in terms of performance in that situation. The performance for the other operations has, in fact, gone up considerably, and integer 8 operations, because they went out of favor with AI, has also diminished. And the real estate, of course, that on the chip has gone into some of those other operations. So that's sort of the situation today with NVIDIA, and it really drives the point home that we need to use some of our technology in terms of mathematics to help us in designing algorithms that can effectively drive through that. So matrix multiply is central to AI. That's the heart of AI algorithms, and that matrix X times W is at the heart of the computations that go on. That's where that tensor core comes in handy. That's why we're interested in doing those matrix multiplications, and it allows the model to combine things in an effective way. AI does not fundamentally need a GPU to do that, so that's something to keep in mind. And it just requires high throughput matrix operations with matrix memory bandwidth, or with high memory bandwidth, to effectively move data through that system. So GPUs happen to have that combination and can do that very well today. But as line shine has shown, perhaps there's another path, and that path just uses CPU and simplifies some of the other issues associated with using these machines in terms of the software and the overall harnessing that's necessary to effectively use them. So I'm just going to harp on this a little bit more. This is our standard way of doing floating point. We have standards that talk about 128-bit floating point, 64-bit, 32-bit, 16-bit floating point operations. Those 16-bit floating point operations are mainly used for machine learning and driving neural networks. And NVIDIA has 8-bit floating point arithmetic, and there's 2 flavors of 8-bit. I guess I just want to point this out as well. One situation where there's 5 bits for the exponent and 2 bits for the fraction, and another which has 4 bits for the exponent and 3 bits for the fraction. And again, that's driven by the AI needs. Forward propagation through the neural network requires higher precision, and the gradient descents require less precision and more dynamic range associated with it. And then there's even a FP4 format that can be effectively used. And from our standpoint, how can scientific computing leverage those ideas, and how can we effectively drive some of the computations that we have? So with mixed precision, less is faster. We're getting faster things because of the reduced memory traffic associated with it. If you're pushing less bits, you can move more of those bits through more of those numbers through the memory system. We reduce network traffic. We reduce the footprint overall, and the arithmetic is usually faster. And if you use going from one precision to another, downgrading, let's say, you usually get a factor of 2 and maybe more as you do that. So here's an algorithm that has some of these characteristics. This is a relatively old algorithm. It's an algorithm in linear algebra. It's an algorithm that looks at solving a system of linear equations, a dense system of linear equations. And the idea is to come up with a factorization, which is the major cost of solving this problem, and do that in reduced precision. So do that as fast as you can with less precision, come up with a solution in less precision, and then use a technique to enhance the accuracy. So the goal ultimately is to drive the solution to the same place you would have been had you used a higher precision to begin with overall. And the algorithm that's scribbled here on this slide is really taking the approximation that you've gained in the lower precision and applying Newton's method to it. So Newton's method has this incredible story in terms of convergence. You basically get quadratic convergence. So if you have an answer and you apply the algorithm, it doubles the accuracy at each iteration of the algorithm. So if you have four digits correct on the first iteration, starting the first iteration, that the next iteration will give you 8 bits correct, and then the next iteration gives you 16 bits correct. So it doubles the number of correct digits as long as certain conditions are maintained. And this algorithm has shown great promise, and there's been enhancements that have been done to this algorithm in terms of even making it more effective and ensuring that the accuracy can be carried out along for a longer time. So an example of how this works in reality, so this is a graph showing the performance. This is on a Blackwell. What we're looking at here, the blue thing is the time and the power requirements associated with solving the problem using 64-bit arithmetic. So using 64-bit arithmetic, we end up with an algorithm that gives a performance around 33 teraflops and consumes 53 gigaflops per watt. And using the algorithm I've just described, it changes the behavior, gets the same accuracy, starts with an approximation in a lower precision, and then does a few iterations that converges to the solution that's as accurate as the blue line, but it runs at 280 teraflops. And it's running a lot faster, and it basically is running 8 times faster and consumes ultimately 8 times less power. So those are the ideas that we're trying to capture and apply to the hardware that we have available. So I'm almost on my last slides here. The hardware is constantly changing. We went from a world where we had scalars to vectors to distributed to accelerated hardware. We have mixed precision associated with it. The algorithms and software advances to follow the hardware. So that's, again, a situation with co-design. We're always following what's done by the hardware to try to use the facilities that have been put in place. And we need a better way of doing that. So there's plenty of room at the top. If you're interested, there was an interesting paper that was published a few years ago by Charles Leiserson, where he talks about a lot of the issues that I've gone over in this presentation, trying to leverage some of the ideas to get a higher level. And of course, it's a takeoff on Feynman's rather famous lecture he gave in 1959 about quantum computing, where there's plenty of room at the bottom in his context. So let me finish with that. There's a bunch of references that you can go to that looks at some of the ideas I've talked about here. Some of the papers are relatively recent, and I'm pleased to answer any questions if you have them. So thank you so much for your attention.
Yeah, thanks, Jack, for the wonderful talk. So if you have any questions, you can post them on the chat, the Q&A part. In the meantime, also, you can walk up to the mics. There's one in each lane. So if you have any questions, please just walk up to the mic. In the meantime, while people think about their questions, I'd like to ask Jack some questions as well. These iterative refinement methods, they somehow limit the dynamic range that you need to handle, and that's why you can use lower precision. So if you were to apply this to like other domains, not just linear algebra, like what would be the key? Like how do you limit the dynamic range of your problem such that you can use these lower precisions? Is this applicable beyond like matrices?
Well, I think it's using techniques like Newton's method that can be applied to other functions is a reasonable way to start pursuing that line. But we need to understand that the reason why it works so well with the linear algebra case was that the bulk of the work was done in factoring a matrix, and that factorization gets used in the iteration process to get the next solution, the next iteration. And we need to come up with ways to leverage that kind of advantage with the situation.
Yeah, that makes a lot of sense. We have one question here.
Yep. So thank you for the nice summary of where we are and where hopefully we're heading.
Can you state your name and where you're from?
I am Marek from Cambridge, from mathematics, not central IT. Anyway, so from it's of course very much of a gut feeling question, but from your experience in the field, how long do you think we've got until we actually start making all this AI thing more energy efficient? Because, like you've said, top 500 is currently very much dominated by commodity hardware. Co-design is a great idea, but unfortunately systems like Lineshine or Fugaku are now very much the outliers. Meanwhile, the vogue for powering those new gigantic data centers, gas turbines, everybody forgot about net zero, and in case you guys haven't read the news, we are experiencing the record high temperatures throughout many European cities now. So the question is, how long is this going to take? I'm not going to ask whether it's going to be fast enough, because probably nobody knows that, but what's your guess? How long are we still going to keep running things by just throwing more hardware at it before starting to do more things more intelligently?
Right. So ultimately, the answer is going to come by changing the way in which our hardware is built. And the way in which our hardware is built is using silicon, and we need to change that to photonics somehow. So having light-based computations would be one way to drive the energy down in a very substantial way, I think. And I think we were going to edge up on that problem. It's not going to happen overnight. It's going to happen over a long period of time. But then, we'd have a situation where we can do those mathematical operations by shining light into some device and having the output from that be the results of multiplication. So shining, in a perfect world, shining the representation of the matrices into this crystal and having the output of that be this multiplication of those matrices. So that drives the energy cost down quite considerably.
Yeah, but roughly, what scale are we talking about?
In terms
Years,
of time,
decades?
It's not going to happen in my lifetime. And then there's always the promise of, dare I say, quantum computing.
Okay. Do we have?
Why not?
Why not?
I'm Nicholas from New Zealand. Hi, Jack. Following a question of the gentleman, which are the bottlenecks in our lifetime? I mean, something a little bit, and could be also geopolitical, could be funding, but we discussed a little bit of co-design and open source hardware in a Birth of a Feather session. Some of us are exploring non-von Neumann architectures. But is this sometimes a management issue? I mean, there are islands of novel technologies, but and we understand that management is an art more than a science, but give me 2 or 3 highlights of things that could be easier to solve if there is goodwill.
So let me just answer your question by reflecting on, when I was a student, there were many experimental machines that looked at different architectures that were done at universities, that were done to help drive the architecture forward. And machines like the Iliac, machines like the systems that came from MIT or from Stanford or from Washington. Many places were engaging in hardware architecture design, which was considered radically different. And I don't see that today. I don't see that being done. I don't see it being done at the scale that would need to be done to enhance or provide us with the capability to go forward. So I think more experimentation like that is necessary. Experimentation where I don't know the answer, so some of those are going to fail. And it's okay to fail in this situation. So we need to realize that we're not always going to come up with an answer that's going to take hold. We're going to have to make investments and understand from those investments how we really want to go forward. And we don't have that. I don't see that kind of investment going on today.
Hello, Mick of Bolt Graphics out in California. Regarding the adoption of mixed precision algorithms, do you think that or do you feel like we've, as a field in HPC, done a good job of extracting the performance of lower precision and yet still maintaining accuracy? Or do you think we need more numerical analytics experts in the field?
The simple answer is we need both. And to drive the algorithm research and to drive the development of the adoption of those within the applications themselves. So there's no one solution that's going to be satisfactory there.
Okay, so we still have a ways to go, you feel, in that regard?
Ways to go, yes, indeed.
Thank you.
Okay, so we have some questions online. One of them, so I'm going to read it out. Thank you for the excellent presentation. What are your thoughts on native FP64 versus emulation via Ozaki 2?
Okay, so I didn't mention Ozaki. Ozaki is a method that emulates the floating point operations. It's been used to do matrix multiply quite effectively. So Ozaki uses a number of lower precision steps to build up a solution, which then has the accuracy of the higher precision results. And by using the lower precision, we get the benefit of perhaps those integer operations to start with, and then come up with a solution. So I think that's a wonderful algorithm, and it's a good area for research. So those are terrific ideas. The issue with Ozaki comes about because of its application. It works very well for matrix multiply. So matrix multiply works, we see the benefit immediately. For other operations, it doesn't happen. So it doesn't work meaning you don't get the improvement in terms of performance for vector operations or for scalar operations. So that needs to somehow change in order for it to be more widespread. The other issue is, if you use Ozaki, the implementations that I have seen and helped implement, they don't respect IEEE arithmetic. So now we're in a situation where it could potentially get into trouble if we're on an edge case looking at not a number, denormalize things, negative zeros. There's situations where we could effectively come up with the wrong answer in that situation. So we need to take a little bit better care in terms of care of doing it. But Ozaki is a great use of techniques to help and to expand the range in which we explore things.
Yeah, just to follow up, do you think it has a lot of practical benefit in like many use cases?
Well, if you have a matrix multiply, it's perfect. So I would say we should use it. And I think in the case of NVIDIA, it is implemented in the software library, so it can be used and is used. And if it gets into trouble because of requiring too many slices, that's a more technical issue. It will fail safe back to the traditional way of doing it. So you lose a little bit of time rather than to get the wrong answer.
Okay. So yeah, I guess we're a little bit close to the end of the time limit. So yeah, let's thank Jack again for his wonderful closing keynote. Yeah, thanks, Jack. Yeah, sorry for the mishap.